Welcome to my presentation about Multipars, reduced communication MPC over Z2k. This is a joint work together with my co-authors Pascal Reissert, Marc Revinius, and Ralf Küsters at the University of Stuttgart, Institute of Information Security. So what is this about? Multipars, this is an offline phase, also known as pre-processing phase for the speeds MPC protocol over Z2k. So to get everybody on the same page, quick recap on the speeds MPC protocol. Here in this talk, I will only talk about the two-party setting, but all of this can be extended to the multi-party setting too. So we have two parties, Alice and Bob, and first they run an input-independent offline phase where they produce some correlated randomness, which is then later used in the online phase to speed it up. And this correlated randomness in the speeds MPC protocol consists of a secret MAC key alpha. So this is just a secret number alpha in our domain, which is secret shared among the parties using additive secret sharing, also known as full threshold secret sharing. And then they will also produce some more correlated randomness, which I will talk about soon. And then later in the online phase, they have their inputs also secret shared. But here, these double brackets notate that these are authenticated shares, which means we don't only have a secret sharing of X, but we also have a secret sharing of alpha times X, which can then later be used to check that the parties didn't tamper with the inputs. So this gives us malicious security, also known as active security. So all inputs and intermediate values and outputs in the end are shared and authenticated. And now let's say we want to, for instance, compute an addition gate, X plus Y. So we somehow need authenticated shares of X plus Y. This is very easy. The parties can just locally add up their shares. So this is nothing new, I think. It gets more difficult when we want to compute a multiplication gate, X times Y, because we cannot simply locally multiply our shares. Instead, what we need to do is, or what we do in the case of the speeds protocol, is we produce so-called beaver triples, also known as multiplication triples, beforehand in the offline phase. So these multiplication triples are just random numbers A and B, and also C, where C is A times B. These numbers are generated and shared and authenticated in the offline phase and can then later be used to speed up this or to perform this multiplication in the online phase. How is this done? This value A is used as a mask for X, B is used as a mask for Y. And then these differences are opened, so the parties learn these values. And now the parties have everything they need in order to locally compute shares of X times Y and also the corresponding MAC tags. So this is called beaver multiplication. And one thing to note here is that we can use such a beaver triple ABC only for one multiplication. We cannot reuse such a beaver triple because here it's basically used as a one-time pad encryption of our secret values X and Y. So we can only use these values A and B once, so for one multiplication. That means in order to compute large circuits, we need to produce many of these beaver triples in the offline phase. And the question is, how can we do that? Of course, a lot of work has gone into this. Here, just recall what a beaver triple is. And there are different ways to do this, to produce these beaver triples. Some of these works are oblivious transfer based, some of them are based on linearly homomorphic encryption or based on somewhat homomorphic encryption, where somewhat homomorphic encryption means that we can also do one multiplication on ciphertexts. We also have to talk about the domain. What is the actual domain where we want to do multi-party computation? So where our values x and y are from. It could be a finite field, ZP for some prime number p, but it could also be a base ring modulo 2 to the k, which enables a more efficient online phase because by setting k to the width of our machine words, our CPU basically does this modulo 2 to the k for us. And when we have this domain, then of course A and B in our beaver triple are chosen uniformly at random from the domain, so we can use it as a mask. So there have been different works. For instance, the mascot protocol, which was one of the first, let's say, practical protocols to do beaver triple generation. It was oblivious transfer based and very fast, but it still requires a relatively high communication. To bring down this communication complexity, there was the overdrive paper, where they showed that beaver triples can also be produced using linearly or somewhat homomorphic encryption. This has been refined in the Top Gear paper with more efficient zero-knowledge proofs, and in the Low Gear 2.0 paper by our institute with a new approach how to actually compute these beaver triples that does not require a so-called sacrificing step anymore. However, it took quite some while before this this overdrive protocol was also generalized to the Z2k setting. And this was the overdrive 2k paper. And this only focused on the somewhat homomorphic encryption-based approach, which is also known as high gear. And the thing is that high gear, so this SHE-based approach, is mainly useful for a high number of parties, while the LHE-based approach, also known as low gear of overdrive, is mainly suitable for a low number of parties, such as the highly relevant two-party setup. And therefore, we wanted to fill in this gap with our work and generalize overdrive to the Z2k setting also in its low gear variant. So this has been published in the proceedings of PETS 2024, and there's also an ePrint report online. This is what I'm going to talk about now. So how does this low gear actually work? For this, we first need to talk about LHE-based oblivious linear evaluation. What is this? Let's say Alice and Bob have input A and B. So Alice has input A and Bob has input B, and they want to compute additive shares of the product of A and B. So what they can do if they have a linearly homomorphic encryption scheme, first note, this is not a beaver triple, because in a beaver triple, A and B are secret shared too, but it's already close. We can later use this also to compute beaver triples. So as I said, we want shares of A times B. So let's call these shares D and E. So what we want is, we want to compute D at one party and E at the other party, such that the sum of these two shares is A times B. So Bob just chooses E at random, and that means all that's left to do is to compute D as A times B minus E. And using linearly homomorphic encryption, Alice can compute a ciphertext that encrypts A, sends that over to Bob, and Bob then multiplies this times B and subtracts using Alice's public key an encryption of E. So now we have a ciphertext for A times B minus E, which is exactly what we wanted. And we send this back to Alice, who can decrypt it as Alice knows her own secret key. And we are done. Yeah. I left out some details, such as the modified encryption procedure here, which is required to make sure that Alice does not learn anything from the noise of the received ciphertext. Also, in the first message sent by Alice, we need to perform a zero knowledge proof to make sure that, or to guarantee that this CA is actually a correct ciphertext. So, how can we use this oblivious linear evaluation to produce beaver triples? Well, first, observe that when we can for Alice's input A and Bob's input B, produce shares of A times B, then we can also do the same when the inputs are already secret shared by using a pairwise protocol. So each pair of parties runs this protocol once. In the two-party setting, this means this is once run with Alice's share of A and Bob's share of B, and once the other way around. So we can multiply shares. So now, how does the Overdrive Low Gear 2.0 protocol utilize this OLE to produce beaver triples? So recall that from the offline phase, or from the setup, we have this secret MAC key alpha, which is already secret shared. And now, let's say we also have A and B. How to produce A and B? That's easy. Just all parties randomly choose their own share of A and B. So Alice randomly samples A0 and B0. Bob randomly samples A1 and B1. But now we somehow need to multiply A times B. And then we also need to authenticate all of these values, A, B, and C, by multiplying all of them by alpha. That's what the original low gear protocol did in this order. However, this required afterwards to do a so-called sacrificing step, where about half of the beaver triples are sacrificed in order to guarantee that the other half of the beaver triples satisfy the correct multiplication identity. The low gear 2.0 protocol therefore slightly changed the order. What it did is, first we multiply B times alpha using, in this case, 2 instances of OLE, so just pairwise OLE. So then we have already authenticated B. And then what we do is we take the value A and we use OLE to multiply A with 3 different values, namely with B, with alpha, and with alpha B. Yeah. If I go back to the OLE slide, you can see that we can amortize easily over multiple A's, because we can simply send over this ciphertext once. This is independent of B. And then Bob can multiply A with multiple values and send multiple ciphertexts back. So we can multiply we can amortize by multiplying one value at one party with many values at the other party. And this is done here in this step, where we have A, which needs to be multiplied by 3 other values. And this amortization at the same time makes sure that if an adversary tampers with the value A, then all 3 of these multiplications are tampered with, which is then later revealed, which then does not only modify so it does not only break the product, but it also breaks the authentication and would then later be revealed in the MAC check. So by making it in this order, we don't need the sacrificing step anymore. Yeah. And then, of course, there's a MAC check that in this MAC check, we just make sure that that actually A times alpha is the same as the share as the sum of the shares for alpha times A, and so on, so that all of these multiplicative properties of the MAC tags hold true. This is required for active security. Okay, so this protocol was in the domain ZP, so a finite field for some prime number P. What if we now try to extend this to Z2k? So now we are over a ring. Now the problem is, in the ring we have zero divisors. We have non-trivial zero divisors. And this will be a problem. Let's say Bob is malicious. In this case, Bob could, before sending back this ciphertext here, add an additional factor of CA times 2 to the t minus 1. Now notice this is a zero divisor, this 2 to the t minus 1, because if we would multiply another factor of 2, it would be 2 to the t, which is 0 again. So this means that that later in the MAC check, this is what we see on the next slide. So what does this attack actually now mean in our Logia protocol? If we add this factor of 2 to the t minus 1 times A, let's say the adversary, Bob, runs this attack on the ciphertext sent back here, which basically gives the share C0 at Alice. Then this share is now tampered with, and then the MAC check, but the MAC check will now fail if and only if A0 is odd. Why is this? Well, if A0 is even, then it would have a factor of 2, so 2 to the t minus 1 times 2 cancels out. So that's 0 again. So we didn't actually tamper with it. So that means from the fact whether the MAC check fails or not, Bob now learns if A0 is even or odd. But A0 is Alice's share, so Bob is not supposed to learn something about it. And now the question is, where does this break in the proof of Logia? In the security proof of Logia, or also Logia 2.0, they assumed this so-called enhanced CPA security property of the underlying linearly homomorphic encryption scheme, which basically means that when a challenger sends a ciphertext to the adversary, and the adversary can then modify this ciphertext and make oracle queries whether this modified ciphertext decrypts to 0 or not. Then the enhanced CPA security property basically states that the adversary does not learn is not able to deduce any information from these queries about the originally encrypted message M. So the adversary can make a polynomial number of these queries, and in the end, the adversary is challenged to guess, or the adversary receives either M or a random message and is challenged to guess which one of these is the case. So if the adversary was able, using these queries here, to learn some information about the original message M, the adversary could now compare this against the received message and then gain a non-negligible advantage in correctly guessing this bit B. And this enhanced CPA security is assumed, for instance, for the linearly homomorphic version of the BGP encryption scheme, but only over finite fields. Because if we are over Z2k, we can easily perform a successful attack by doing basically the same again, which was also done in the previous attack on the actual protocol, just choose Cj as 2 to the t minus 1 times c, and then from whether we get OK or fail back, we basically learn whether the message was even or odd. So how can we fix this in the Logia protocol over Z2k? So what we want to compute is beaver triples over Z2k, or actually Z2k plus s. This additional plus s has to do with the fact that our max need to be computed over a slightly larger ring, but that is out of scope for my presentation. But if you know Z2k, then you already know this, that we have these additional plus s there, so additional s bits for the max. And now our fix is to produce beaver triples over Z2k plus 2s instead. So we add another s bits here, and then the previous attacks, which I just told you about, they make it possible for the adversary to learn the least significant bit of certain values. Yeah, so if the adversary learns whether something is even or odd, that's the least significant bit. Or if you generalize these attacks, the adversary can also, with degrading success probability, learn more and more bits. So some least significant bits can be learned, but we cut off the least significant S bits from the resulting beaver triples using our new truncation protocol. And then we obtain again beaver triples over Z2k plus s. And all of the bits which might have been leaked using selective failure attacks are now thrown away anyway. I don't have time to go into details about this new truncation protocol, but we of course also proved that our adapted protocol is secure by introducing a new security notion called 2S enhanced CPA security. So it's now 2S enhanced, and this is the previous security game. But now what we changed is here in the bottom left. Instead, in the b equals 1 case, instead of giving the adversary a random message, we give the adversary a random message, but where the least significant S bits are still the same as in the original message. So basically, this security game formalizes that the adversary is always allowed to learn the least significant S bits of the message M, but only after making those queries. We also made some further optimizations to bring down the communication complexity of our protocol, namely adaptive packing, which means we use different techniques for different packing techniques for different parts of the protocol. So this has to do with single instruction, multiple data. In BGP, you typically encode multiple plaintext in a single ciphertext, and there are multiple packing methods that can be used to do that. And we use the coefficient packing for this OLE, which is possible because this alpha is constant and is the same for all values, or for all beaver triples which we produce. And for the amortized OLE, we then use the tweaked interpolation packing, which is required to do component-wise multiplications. This is also an optimization that would not be easily possible in the high gear variant, because there we cannot easily switch between those packings. But in the low gear variant, this is easily possible. Also, we introduced modular switching in the OLE. Here, the first ciphertext which is sent has to have a certain high parameters to guarantee security. But then we can use a modular switching technique to basically, let's say, compress the ciphertext that is sent back. So that saves on communication too. And for the zero knowledge proofs in this OLE, we use a rejection sampling technique, which also means that we can reduce the parameters of the zero knowledge proof at the cost of that the zero knowledge proof might need to be repeated in certain cases, but that doesn't happen so often. And in total, that means that our protocol multipars in the two-party settings is, in terms of kilobit per triple produced, more than twice as good as the prior work for Z2k. And we also implemented Multipars in the Rust programming language and performed extensive benchmarks, where we see that especially in low bandwidth settings, which are very relevant in case of hosting it in the cloud, where bandwidth might be very expensive, we outperform the previously implemented Z2k protocol from MP Speeds. So that's it. Here are my references. Can you look here at the PETS publication, the implementation, or the ePrint report. And for these citations, which I had in brackets, also please look at the ePrint report. So, thank you.